Greetings, everybody. Let's talk a little bit about linear independence. So recall in the definition that if we had a collection of vectors v1, v2 up to vn, then we say that those are going to be linearly independent if we take a collection of scalars c1 up to cn, we take the linear combination and it's 0, then we know that the only way that could have happened was for all of the coefficients that we selected to be 0. Now, we can make the connection between linear independence and linear transformations in the following way. What we can do is take our collection of vectors v1 up to vn, and we can define a function t from n-dimensional real space, so into our vector space v, such that t of c1, c2 up to cn, so t of that vector is going to be sent to the linear combination of ci, vi. And so what we do is we claim that this is going to be a linear transformation. Well, how do we check that? We have to make sure that we respect vector addition and scalar multiplication. So if we take two vectors in Rn and we add them together, well, that just gets added together component-wise. We then apply our function t, and so we get the sum of the quantity c sub I plus d sub I times v sub I. Well, then using our distributive property in our vector spaces, we can distribute that v sub I to each one of those, and then we can split up that summation into a summation of c sub I of v sub I plus the summation of d sub I of v sub I. And the first summation is t applied to our first vector. The second summation is t applied to our second vector, and so we do respect vector addition. If we do the same thing for scalar multiplication, well, a scalar times that vector just does it component-wise. We apply t, so we get alpha c sub I times v sub I. Well, again, this next property is another property of associativity of scalar multiplication. So that's going to be the same as our scalar c sub I times v sub I times alpha. We factor out our alpha, and so we get alpha times t applied to our original vector. So that shows that t is going to respect vector addition, it respects scalar multiplication, so t sure enough is a linear transformation. Kind of a set that we had talked about before. If we look at the kernel of t, well, that's our set of vectors such that t of that vector is going to give us 0. Well, since t of that vector is just our linear combination with the v sub I, what this is really saying is that the collection of vectors, the collection of scalars that give us a linear combination of 0 is going to be the kernel of our transformation. And so kind of the conclusion that we can draw from that is that v1, v2, vn are linearly independent if and only if the only linear combination that gives us the 0 vector is the 0 vector itself. So all of our coefficients have to be 0. So our kernel of t, so this is kind of one way of looking at taking our vectors, performing a linear transformation, making a linear transformation out of them, looking at the kernel, and then that kind of helps us decide whether or not that collection of vectors is going to be linearly dependent or linearly independent. So now we want to try to make the connection with matrices. So now if we've got, again, our collection of vectors v1 up to vn, and these are in m-dimensional space, well, let's denote that by v1, our components just being v1's, our subscripts being the subscript of the vector, and our superscript being the component for that particular vector. So v1 looks like this, v sub 2 looks like these, v sub n looks like these. Well, if we then take the m by n matrix whose columns are the v sub I, then we get an expression that looks like this. We multiply that times our column vector And the property of those linear, property of that matrix multiplication, we can write this thing as C1 times our first column vector plus C2 times our second one, all the way up to Cn times our last column. But that is C sub I times V sub I, our sum of those. That is the value for our linear transformation. So if we take our vectors, we make them column vectors, then we can multiply by our coefficients, and that gives us our linear transformation. Okay. Now, kind of rounding out this video with a property of this linear independence, that our set of vectors v1 up to vn are linearly independent if then for each w in the span, and remember what the span is just all possible collections of linear combinations of these guys. So an element w is in the span, then the expression that we would get for that thing being in the span is unique. Okay, let's kind of see why that might be true. So suppose that for some w in the span that we've got two different representations as far as coefficients for w in there. We've got C sub I times V sub I, and we've got D sub I times V sub I as being two different bunches of coefficients that two different linear combinations that give us w. Well, if we just do a subtraction on those, then we get 0 being all of those linear combinations. We combine like terms with respect to the V sub I, and we get a linear combination that gives us 0. But we said, and we had the assumption that the V sub I are linearly independent, and so what that means is the only way this can happen is for all of our coefficients to be 0 to begin with, and so C sub 1 minus D sub 1 is 0, C sub 2 minus D sub 2 is 0, all the way up to C sub n minus D sub n is 0, or C sub I is equal to D sub I for all of our I, thereby making the expressions unique. We can't have two different bunches of coefficients that give the same vector when the set of vectors that we're dealing with are linearly independent. And so this kind of brings us to the close of our first discussion on linear independence. I hope you guys have enjoyed it, and I'll see you guys next time.